right. So today we are going to do some chapter 1 chemistry for MCAT review. And now, I'm not going to lie, chemistry is not one of my favorites, but I think we can manage. So we're going to start with some math and measurements, kind of pretty much how to put it all together. That way, we're going to talk about subatomic particles for the nucleus. We'll go into atomic number and mass, ions, isotopes, decay. The decay will kind of be directly branched off of the subatomic particles. We'll talk about half-life, also with decay. We'll talk about the Bohr model. We'll talk about orbitals, quantum numbers, a lot of the principles like the Pauli exclusion, Aufbau, and Hund's rule, diamagnetic, paramagnetic, and periodic trends. So I guess let's just get into it, So to start, we're going to deal with a lot of the measurements. So for measurements and for scientific notation, these are pretty much just unanimous across the board. They like to work in threes, I've noticed a little bit. So if we have like kilo, deci, centi, milli, micro, nano, and pico. And these are used a lot, especially with their symbols. They go pretty much like this. And then the scientific notation, they like to use a factor of 10. So it'll be like 10 to the third, 10 to the negative 1, to the negative 2, 3. And then this is where they just kind of jump to 6, 9, and 12. And that just happens a lot. And these are a lot of the normal factorials that you'll see and use. Sorry, this is super far. These are the normal factorials that they'll use pretty consistently. Yeah. And so then that goes hand in hand with like the physical quantities. So if we're talking about length or mass, time, current is going to be big for physics, temp, number of particles, and like luminous intensity, which is, I don't know, I've never really seen a ton of it, but I'm sure it'll come up later. So length uses meters, mass uses kilograms, time's usually in seconds, current's in ampere, temp is in Kelvin, number of particles will be moles, and then luminous is candela. And so what I've used the most is going to be like iterations of mass, length, not too much in chemistry. This is just kind of like the metric units. This is more physics and these. So like knowing kilograms, grams, milligrams is going to be huge. Kelvin is just based off of the 273 Kelvin. And then the number of particles for moles, that'll be big for molarity. And so a lot of the normal equations that you're going to need to use, especially in chemistry, you're going to need to know volume. You're going to need to know a lot of conversion units. So volume is just length times width times height. And so depending on what you're using, this is three-dimensional. Like obviously times when people just do like 2D squares, like just length times width. That's area. Yeah, volume is three-dimensional. So you're going to have m cubed for that because it's length times width times height, 3 dimensions. You're going to use that. And from there, you can just pretty much manipulate like meters to centimeters to decimeters, and then it's to the third, so you would have to square things. We'll kind of go through that later on, but just know like there's a lot of different ways that you can move across those. And also, again, this is me synthesizing a lot of the information that I have when I'm studying, so I'm just kind of going through especially what I need to work on specifically, and if someone ever wants me to do more, I can easily do that, but that's what this is. So volume is here. Density is mass over volume. And so volume, I believe, is usually used for liters depending on what you're working with, depending on certain things. So I know like for molarity. It's volume for like L density. It kind of depends. So it could be like m to the third liter, I think. Mass is going to be in kilograms or grams, but just as long as it's kind of unanimous throughout, I think it's fine. Now, when we're going through chemical compounds and stuff, you want to know what percent of something there is. So if I have water, so like H2O, if I want to figure out what percent of mass for hydrogen is out of this entire thing, I would use mass percent. And so what mass percent is the mass of component. So in this case, it would be my, well, it's H2 over the mass of the total, which is H2O. And then that will give me some decimal number, and then all I do is multiply that by 100, and that'll get my clean percentage. And sometimes use parts per million. I haven't seen it too much, but parts per million is just 10 to the 6th. So whatever number you would get, you would just multiply times 10 to the 6th, and it'd be pretty easy from there. Another one that you're going to have to use, especially for like biochemistry, when you're putting buffers together or when you're making a lot of solutions, you have to be very confident in your molarity and knowing kind of how that works. So our molarity is M, so moles, mole over volume liter. And so again, that mole is just the amount of substance that they had. They've gone through and they figured out how to pretty much calculate all of that, which we can go through later, but again, it's not necessarily that important at the moment. So there's conversion factors, mass percent we talked about. Now empirical versus molecular formulas. Again, I just want to start with the math part because everything kind of builds off of the math, and we can kind of go into the conceptual stuff later. So there are two different things. One's the empirical versus molecular formulas. The empirical formula is low ratios, while the molecular is the actual ratios. So for instance, the empirical formula that I could have is like, and then this is just like random stuff. Cl, I could have like Cl4, I'll just go C2, Cl4, O8. Now this is like never would happen, just it could never conform this way. I'm just writing down absolutely random numbers. However, this could be the empirical formula, but the molecular formula could be completely different, depending on like the amount that I have. So say I have, these are just the ratios. So say I raise it by a factor of 6, I would end up with C12, Cl24, O48. Again, just random arbitrary numbers. None of this would actually matter. But it's for empirical and molecular, just remember it's the ratios that are important. And so going back to the moles. Now, 1 mole, remember it's the amount of something. So 1 mole could be a certain amount of particles, and that number of particles is Avogadro's number, or as I like to joke, avocado's number. So we use 6.022 times 10 to the 23rd molecules per 1 mole. And then this is a good conversion factor. So if I know for a fact that I have 28 moles, I can easily figure out how many molecules I have by just simply multiplying by Avogadro's number. That's how I would know how many particles were in that mole. And it can go from there. It's based off of carbon. Again, it's not super important. However, it's stuff that you need to know. A lot of the stuff with basic chemistry or general chemistry in itself it all comes down to ratios, and especially when it comes to stoichiometry. stoich. Is it IO? Yeah. Stoichiometry. And so, say I have a molecule of water, H2O. For every mole of H2 that I have, there's 1 mole of H2O. Or if I have, like, you can go in so many different directions. It can be for the entire thing. It can be for 1 mole of H2 that I have 1 mole of oxygen, especially when you're going into limiting reagents and whatnot. But it's just a way of conversion factors. And so molarity, we talked about its moles over liters. And I'm sorry I'm all over the place, but I'm just trying to figure out how I'm going through. I'm just going through all the math right now. When we talk about molarity, M, specifically, it's moles of solute over solution volume in liters. This is what we talked about over here. I don't know where I wrote it. Yeah, so this moles is specifically for the solute. And you can do, again, a lot of conversion factors within that. Okay, I think that's pretty much all the math we need to talk about right now. It's just basic stuff that we can expand on, and we will expand on because I need to work with some of the basic math, which is pretty dumb. I don't like it. But the molarity you're going to need to use, you're going to have like formulas like M1 V1 equals M2 V2 when it comes to titrations and all that good stuff. But these are kind of like the underground principles of the chemistry and math. Now, let's get to the good stuff. So I think it's most fitting to start with the subatomic particles. Sub meaning smaller, atomic meaning atom, so smaller than the atom. So you're going to have our neutrons, protons, and electrons. Okay. If you don't know, within an atom, this goes into Bohr's model, but I won't go too deep into that before it's time. In the middle of every atom, there's going to be this part of space where there's a condensed amount of subatomic particles. This houses our neutrons and protons. So, thing to know about neutrons, they do not have a charge. Protons, on the other hand, have a charge of +1. Electrons are the counterparts to the protons. They're not the same in size. However, they like to be around this nucleus, that space where the neutrons and protons are, and they like to live in space, and these have a -1 charge. So, those are the charges of the subatomic particles, but what do they actually do? Neutrons have some amount of weight, as well as protons. So they are going to be the chief, how do I say this? They're going to be the main contributors into the weight of the atom. The electrons, their weight is pretty much negligible. There's not much going on there. So when a certain atom has mass, it is taking our number of neutrons plus our number of protons, and that gives us atomic mass. Now, when you go to a periodic table like this, there's going to be numbers underneath, and these are ones that you're going to see a lot like on the MCAT. These numbers right underneath, they are the atomic mass. And what they do is they took all of the isotopes, and isotopes, let me explain quickly, are variations of each element, basically just changing their mass. So I can have one molecule of carbon here, one molecule of carbon here. This one's slightly heavier, and all of a sudden this becomes the isotope of this normal carbon. So they took all the isotopes, they averaged it out in proportion that they are found in Earth's abundance, and they came up with these numbers. So I'm not going to go through the math. It's not that important. However, if you look above here, we have atomic number. Coincidentally, when we have atomic number, that tells us how many protons. So basically, the atomic number is based off of the amount of protons that are in that atom. And because we know atomic mass is neutrons plus protons and atomic number is just protons, it's easy to figure out what our proportion of neutrons are because all we have to do is subtract the number of protons. And so that is how they are loosely organized. Now, because atoms usually have a neutral charge, they will have an equal amount of electrons. Because we do not want our normal, just basic carbon atom to have a positive charge all over the place, we need to even those out. So the proportion of protons to electrons in a neutral atom is equal. However, ions are when we have more of one or the other. So if I have more electrons than I have protons, then all of a sudden the ion or an anion has a negative charge. And then if it's a cation, I have more protons having a more positive charge. And ions are especially reactive because they are wanting to even out those charges or just move in certain directions along that electrostatic line. And then we can go through and talk about mass spec, but it's not super important. However, when it comes to subatomic particles, what is important is radioactive decay. So a lot of this is stable on its own. However, certain times, some atoms just aren't. And so a lot of these subatomic particles can be released, they can be accepted, and a lot of different things happen. So if we start with alpha decay, and this is going to take me some time to get used to it, like what they are, because I'm reviewing. It's actually 2 protons and 2 neutrons being expelled, I believe. Yes. So it's 2 protons and 2 neutrons pretty much leaving the nucleus and just say, hey, see ya, smell you later. Coincidentally, the element that has 2 protons is helium. So you're pretty much losing a helium atom with 2 extra neutrons, and it's saying see you later. Beta decay. A little differently. And again, these are just unstable atoms that are pretty much shedding a lot of the subatomic particles, releasing energy and or accepting energy. So beta decay, there's 3 different types. There's beta minus, beta plus, and electron capture. So, oh geez. So beta minus is when a neutron actually becomes a proton and ejects or gets rid of an electron. And so this is actually pretty weird because when this part happens, beta negative or beta minus actually takes atom 1, whatever it could be, and turns it into atom 2. Because remember, our definition of what an atom is pretty much the amount of protons within the nucleus, and it goes from there. And in order for the charge to be the same, an electron and an antineutrino actually gets ejected. So there's that. Let's see what we got. Beta plus. So a proton, this is actually the reverse. Proton becomes a neutron and ejects a positron. And these positron and neutrinos are just other subatomic particles that you don't see too much of. But when this happens, again, we are changing from atom 1 to atom 2. But the biggest difference is the atomic number actually increases without a change in molecular weight. The same is not said here. Atomic number decreases without change in weight. So those are kind of like two sides of the coin. I guess that's why it's minus and plus. And plus, can't talk today. Minus, you are losing an electron and you get a proton out of it, and the other way around. Electron capture. Let's see. So a proton captures an electron and they just take into it and it neutralizes the charge. So you're going from atom 1 to atom 2, but now it's the molecular number decreases. And it's nothing else is being ejected, nothing's ejected. It's just you're accepting an electron and changing that proton to a neutron. Now, what I am stuck on is if you're releasing for beta minus decay, an electron's getting shot out. How does it keep the normal charge? I'll just look into that. Okay. Half-life. Pretty simple. Half-lives, it's a negative exponential curve. If you were to plot it out, pretty much looks like this. That the faster, something decays faster early on than later on. So it's like within a fraction amount of time, that's half the amount of time that it decays, that's your half-life. And it just keeps going and you measure it in half-lives. It's not super important. All you really need to know is the beta decay, all that stuff. The half-lives that you can do, it's pretty easy if you just do fraction remaining equals 1 over 2n because it's that exponential decrease. Okay, now the fun stuff. I mentioned Bohr's model earlier. So before they just thought everything was just moving in space, so the protons, neutrons, electrons, they're all just kind of swirling around. Bohr came out with this idea. So we have a nucleus here, and then the probability that electrons were in space were deciphered to be kind of in these general areas that they call orbitals, or orbits, I'm sorry. And you're going to find electrons probability-wise around these general areas. And so people often just write Bohr's model like this, where n1, 2, 3 are the shells or the orbits, and the electrons as just like negatives kind of swirling around. So it's basically like planets revolving around the sun and going in that direction and kind of going that way, just how it moves. Except imagine Earth, we didn't actually know where it was. It was just probability-wise somewhere around the orbit. I know it might be confusing, but it just goes into kind of, what's the word? Not string theory. Quantum mechanics. Because you don't know the probability of necessarily where it is. Not super important. What is important is for absorption and energy. What it really is just electrons moving orbits. So if I go from high to low, so I have n equals 3. If I'm going from an area of high energy to an area of low energy, I'm releasing a photon out, which is light. Now, the proportion of n equals 3 to n equals 1 versus n equals 2 to n equals 1. This is more energy. This is less energy. Because there's just a bigger difference. The way I think about it is like if I jump off a 5-foot ledge down to the ground, I'm going to feel more impact. There's more going on. It's a higher energy. If I jump from a 2-foot ledge, there's less going on, less big of a difference. So more energy, less energy. But with photons, they're particles, but they relate to waves of light. So if there's more energy being released from high to low, that means I actually have a smaller wavelength. And this is going to go into Planck's constant and going into physics and stuff, because I think it's like C equals lambda over don't remember off the top of my head, but just know that a small wavelength means high energy, large wavelength means lower energy. And so when the photons or when the electrons moving orbits from high to low, it spits out more energy and it's a smaller wavelength. And so if we have smaller wavelengths on a spectrum, almost UV spec, so if my wavelength is like 400 versus 500, what's the orbits? Where would I assign the orbits of like N3 to N1 versus N2 to N1? Well, I know N3 to N1 goes with a smaller wavelength, and that way it kind of gives us an idea of how the electrons are moving. Now, if you wanted to go the opposite way, if I wanted to go an electron from N1 up to N3, we would have to put energy in. And that electron moving from N1 to N3, that would be an excited state, very unstable. However, can be done. So it's just reverse. If you're moving down, you're spitting light out. If you're trying to move up, you have to put energy in. Now, I talked about this a little bit before. It's very hard and pretty much impossible to know where an electron is or how fast it's moving at the same time, or its momentum. So its position, momentum, you can't know both. It's just one of those phenomenon that's pretty crazy within chemistry. You can know one, not the other. So they came up this diagram of orbitals, and these are just a graphical representation of the probability that where electrons could be. Sorry, the camera dies every once in a while. So these are graphical representations of where they could be. So an s orbital is like super small shells, and their image is just like a big ball. It's the best way to put it. P orbitals, you kind of have this dumbbell shape or kind of like a figure 8, and these are in the XYZ plane, so they're three-dimensional. So this has three-dimensionality to it. And then the d orbitals, you kind of have this clover look where it's like 2 8s pretty much put together, and they can go in a bunch of different orientations. So if this is like up straight, you can put it to the side. You can put it, depending on where it is, they can go in all different ways. The important thing is they can go in many different directions, and these are the general shapes of S, P, and D. That leads us into quantum numbers. So the principal number is known as n, and this is the main energy level of the shell. So like if I'm in orbital 1, n equals 1. If I'm in orbital 2, n equals 2. Okay, it's pretty simple. That's bare bones. L is the angular momentum. So that's a subshell. These are like the subshell. That's SPD. So L is pretty much n minus 1. And then the magnetic quantum number, so that's ML. These are the three-dimensional orientations of orbital, and it just gives different values from negative L to positive L. So if I'm starting in shell 1, my L is 0, there's no ML. If my shell is 2, my L would be 1, so it goes from negative 1, 0, 1. Then MS just talks about the spin of electrons, and that's plus 1/2, minus 1/2. Because electrons can be either spinning up or spinning down, and that's how they designate it. The Pauli exclusion principle pretty much says that for 2 electrons in an orbital or in an orbit, one has to be up, one has to be down. That's all there really is to it. And the off-bow principle pretty much says fill the lowest orbital before you move up. Again, pretty simple, and we're just kind of buzzing through this. And I mean, those are pretty much it. And the last one, I'm sorry, is Huns, and all that says is for if you're having 2 electrons in each orbital, it'd be spin up, spin down, and it just alternates. So the next video I'll probably go into the periodic trends, or the next live stream I'll go into the next periodic trends, and kind of all of that thing, all of that stuff. But we got to a good amount. The periodic trends will be its own thing. So